Greetings, my loyal subjects, and I am the king of Chemlandia. And I have terrible news for y'all. I've fallen ill. So, to continue our great nation, I'll now pass on the knowledge of the history of the periodic table to all of you. So to begin, in 1669, the first element, phosphorus, was discovered. And do you know why, my loyal subjects? Because they were trying to create something great, a philosopher's stone, able to turn any metal into gold. But they're not messed up terribly! So they blew things up and phosphorus was discovered. And then a man named Antoine Lavoisier wrote a list of 33 elements that were discovered in order to greater understand the world around us. Continuing this trend, in 1864, a man named John Lewis divided the 56 elements that we had discovered, the knowledge we had acquired, into 11 groups. Following down, Lothar Mayer made a rudimentary table of sorts to help us out in our endeavors, so we could further expand on this knowledge of the elements. And then a great man, Dmitri, in 1869, arranged the 63 known elements as atomic mass. But this still caused problems for us. And then in 1914, a man named Henry Marley provided the atomic number, the proton number, if you will. And we decided to use that to organize our periodic table of elements. And to this day, we still use this model. But now that you understand the history, you need to understand how the actual table works, the different key functions of it. You know, so you don't run around like a bunch of idiots. Because I'm trusting you with this nation, guys. You better not let me mess up. Well, I'm coming up from my grave. Alright. So we organize them into 18 vertical columns, 8 of which are follow the standard groups, and then the 10 of the transition metals. They don't follow a strict pattern, but we include them nonetheless. They have the same amount of outer electrons and have similar properties. Sort of like if you had a big family. Everyone's similar, but no one's the same. So that's how we would include groups. Next is periods are the horizontal rows of the periodic table. And as you move from left to right in this period, you'll notice that the properties tend to change. On the left side, you have the metallic elements. On the right side, you have the non-metallic elements. So as you move from left to right, the element in question either gains or loses its property depending on which way you're going. Let's say you're going from left to right. You'll notice that the element slowly stop losing its metallic properties and start gaining non-metallic properties. So that helps us understand the element in question. Knowledge. As you've noticed, I've been saying the outer electrons, but there's an actual name for this, so I don't want you all going around saying outer electrons, outer electrons. No, that's not right. They're called the valence electrons. And moving on, as you might see in graphs, it seems that electrons go in a circle pattern. This is actually not true. They don't go in a circle pattern around the nucleus, but around in their own little orbits, or orbitals, as we like to call them. And now, I will conclude this message, and we will bring you Chemistry Man.
Hey guys, so now we're going to be talking about the trends in the periodic table. The first trend is the atomic radius, which is the distance between an atom. The size gradually decreases from left to right across a period of elements. This is because within a period or family of elements, all the electrons are added to the same shell. The next is the ionic radius. It is the radius of the atom's ion. Similarly, the charged ions tend to decrease in size across a period and increase in size down a group. The next one is ionization energy. It is the amount of energy required to remove the most loosely bound electron of an isolated gaseous atom to form a cation. Conceptually, ionization energy is the opposite of electronegativity. The lower this energy is, the more readily the atom becomes a cation. Alright, next is the electronegativity, which is the measure of the tendency of an atom to attract a bonding pair of electrons. From left to right across a period of elements, the electronegativity increases. From top to bottom down a group, the electronegativity decreases. Now we'll be talking about the S block. The first part of the S block is the hydrogen. It is the lightest element, and despite its stability, hydrogen forms many bonds and is present in many different compounds. Regular usages of this element is in the chemical industry, where it is used to make ammonia for agricultural fertilizer and methanol. Next is the alkali metals. These metals are characterized by being silvery, very soft, and not very dense, and having low melting points. These metals react extremely rigorously with water and even oxygen to produce energy and flammable hydrogen gas. The elements within this family are sodium, which is used in common table salt, and potassium, which is used in fertilizers. Next is the alkaline earth metals. Like the alkali metals, the alkaline earth metals are silvery, shiny, and relatively soft. The S-block elements are famous for being ingredients in fireworks. The elements in these families are strontium, which is used in fireworks, and radium, which is used to treat certain types of cancer. I seem to be developing an illness now.
P block elements contain p electrons in their valence shells. Most of the P block elements are non-metals. They impart no characteristic color to the flame. Sitting right beneath tin is lead, a toxic metal with an intriguing history. Ancient people used lead for a variety of things, from food, sweeteners to pottery glazes to eating utensils.
Go.
Knowledge.
Properties of the D-block elements. These elements are called transition elements, as they show transitional properties between S and P-block elements. Most of the D-block elements are metals. Transition metals, for the most part, are good conductors. They are also malleable, ductile, lustrous, and are silver white in color. Most are not found in pure substances, but rather in compounds buried in the Earth's crust. Knowledge.
Knowledge.
Earth block elements are called inner transition elements. They are called lanthanides and actinides. Actinides are the elements in which last electron enters into the 5f orbital. All lanthanides closely resemble lanthanum. Lanthanoids are chemically similar to each other, except for cerium and europium. Most lanthanoids are widely used in lasers. These elements deflect UV and infrared electromagnetic radiation and are commonly used in the production of sunglass lenses. Actinides are radioactive. These are highly electropositive. These elements are tarnished in the air. They have a number of isotopes. Similarities between lanthanides and actinides are that both are electropositive and very reactive. Both are paramagnetic.
Knowledge.
Now I have passed on my knowledge to you, so may I continue being great chemistry king and queen. My time is near, and with your time is not. Remember the knowledge that we have passed on to you. Remember the knowledge.